Okay, well, our next speaker is Yoshua Bengio from University of Montreal. And I'm guessing that most of you know who Yoshua is, but I'm going to introduce him anyway. So Yoshua is one of the pioneers of deep learning and one of the people often credited with the explosion of AI, and I think rightly so. He's a professor at the University of Montreal. He's the founder and scientific director of Mila, the Quebec AI Institute, and he co-directs the CFAR Learning and Machines and Brains program, as well as the Evado Institute. He was awarded the Killiam Prize in 2019. He's a fellow of both the Royal Society of London and the Royal Society of Canada. He's a Knight of the Legion of Honor of France and officer of the Order of Canada. And he's also one of the founders of the Montreal Declaration for the Responsible Development of Artificial Intelligence. And I must say, just on a personal, I'm proud to say that I knew Yoshua before he was a superstar. And I got to say, I was pretty impressed back then already. So, so thank you, Yoshua. Yes. Eric wants to say a few words. Oh, okay. I'm sorry. Okay. Yes.
Bonjour. Hello. I'm Eric Brunel, president and co-founder of Druid Informatique, who produces the software Antidote. I'll do a short resume in English, and then I'll switch to French, sorry. I have known Yoshua for more than 30 years. I also knew him before he was very popular, should I say. And I have been impressed with his achievements over the years. Well, I'm here today to pile on another one, which is the formal induction of Yoshua Bengio into our dictionary. Alors, j'ai connu Yoshua à l'époque quand il travaillait là-haut sur la montagne, dans un laboratoire tout petit avec une poignée d'étudiants. Et il travaillait à ses réseaux neuronaux, bien sûr. Je m'étais dit à l'époque, avec nos ordinateurs séquentiels, nos petites mémoires d'1 ou 2 mégaoctets, il n'ira pas bien loin. Eh bien, il avait une vision, il y croyait, il a insisté et il a eu raison. Aujourd'hui, Yoshua a changé le monde. Ce sont des milliers d'étudiants et de chercheurs de haut calibre qui accourent du monde entier pour venir s'éclairer à sa lumière. Et ce sont des millions de gens qui bénéficient des travaux de tout cet équipage. Alors, c'est une grande joie et un honneur pour moi d'introniser aujourd'hui officiellement Yoshua Bengio dans le dictionnaire d'Antidote. Désormais, les utilisateurs d'Antidote pourront citer le travail de Yoshua sans encourir ces petits soulignés rouges du correcteur et ils pourront également consulter la définition de son nom dans le dictionnaire. On n'est pas terminé. Cette définition, je l'ai ici, je tiens à insister sur un point. Elle insiste sur 2 aspects. D'abord, l'immense mérite scientifique de Yoshua, mais aussi sa très grande humanité. Alors, Yoshua, au nom de nous tous, merci beaucoup et bonne continuation.
So finally, Yoshua's title for his talk is GFlowNet Frameworks for Theoretical Neuroscience.
Thank you, Paul. Thank you, merci, Eric. So I want to tell you today about a new neural net framework that we've come up with in my group over the last year and a half. First paper was published at NeurIPS in 21, and how it may connect in interesting ways with the sort of questions that we're asking in theoretical neuroscience. And I'll talk mostly shortly about how these ideas could be used to develop new biologically plausible mechanisms for credit assignment in a way that could replace or complement the existing proposals for alternatives to backprop in the brain. And, but for the most part, I'll talk about how GFlowNets might be an interesting tool to implement the kind of high-level cognition reasoning that, that is happening in human brains, and that we don't have sort of equivalent in modern deep learning. And I think that would be useful for deep learning, but also going to help us sort of get a sense of how mechanically these high-level computations could take place. So that's what I want to talk about. Oh, and as part of that, I'll talk about a new theory that I'm working on with colleagues here, Jonathan Simon, Guillaume Lajoie, Eric Elzino, who's online, Shuji, and others, on how a point of view about the dynamics in cortex at the time when you become conscious of something could help us understand some of the properties of subjective experience and consciousness. And of course, that's connected to the GFlowNet idea as well, because that might be a way to implement that, mathematically speaking. All right. So this is the paper I told you about last NeurIPS. It was actually led by my son, Emmanuel, and my colleague from McGill, Doina Prika, and others, Mark and Maxime. What it is about is, in that paper, we kind of connect with the literature in reinforcement learning. We see GFlowNets as a special kind of reinforcement learning method where instead of trying to have a neural net that tries to maximize a reward, we're trying to see how we can train a neural net to sample stochastically through a sequence of actions. And now you're going to think of these actions as internal actions, like what's going on with attention in your mind. A sequence of internal action that can construct an object. So in the paper, the object is a graph. We're trying to do drug discovery with molecules, but really from the cognitive point of view, you should think of the object we're constructing as some internal representation of a thought, like a sentence or something like this. And I'll come back to that. Okay, but the big thing is it's not a thing that optimizes, it's a thing that samples according to some reward function, and I'll talk more about what the reward function could mean. So it's connected to a lot of literature in generative neural nets, and it's connected to classical literature in probabilistic methods. Like one way to think about it is it uses learning to learn to sample from a very, very complicated distribution that could be highly multimodal, and in that sense can replace classical methods that were used for sampling, like Monte Carlo Markov chain methods, but exploits learning to do it much more efficiently when learning can exploit structure in the distribution. And unlike a lot of generative models, it's really meant to construct complicated objects compositionally, right? So again, this is connected to higher level cognition. So we can have a sequence of steps to construct something. And it could be steps like adding elements, like if you want like edges or nodes in a semantic parse, or it could be steps as in transforming, like if you have dynamics, you have a state and you gradually transform it to achieve something. So all of these can fit in there. And let me move on. Right. So yeah, I'll just say that this framework is actually quite powerful, and we're starting to understand how we can take advantage of it. But one thing it does from a probabilistic learning perspective is it allows to estimate quantities that were thought to be intractable. I mean, that are intractable if you try to estimate them perfectly. So things like partition functions summing over an exponential number of configurations. And thanks to that, you can compute things that are called free energies, which is just, again, summing over an exponential number of things implicitly, right? You never have to actually run these sums. And then you can use these to answer questions about partial statements about the world. So one of the problems that is hard to deal with in probabilistic inference is when the latent variables is just too big an object. All of the things you could say about an image, for example, is a huge set that you don't want to enumerate. And you can use GFlowNet mathematical machinery to train neural nets that can express these probabilities or equivalent energies or free energies in a very efficient way. And then you can use that by taking ratios of these or differences to estimate conditional probabilities that are otherwise intractable. Okay, now let me go back to this question of what is this reward function that we're using to drive the learning of the neural net. Usually when you train a generative model, you give it examples, okay? But here it's different. This is not like, we're not trying to imitate some data set. We're trying to sample in a way that's aligned with some scoring function, which I call the reward function. So that reward function could contain many things, but in particular, it could contain information about how the world works. So you can think of it as a world model. One interesting hypothesis from a machine learning point of view is this separation between how the world works and how we should think about it, how we should take decisions, where we should attend, given the limited budget that we have with the bottleneck of the working memory. And so this is learning a policy that is consistent with an energy function or a reward function that tells us about the regularities that exist in the world. And one hypothesis I have is that this is a hallmark of higher level cognition in at least some animals, including humans, that are not just learning a policy reactively based on the data that's coming, and which makes a lot of sense for some of the things we do, and that lower level animals certainly do, but it allows us to learn without actually doing anything from trying to build decision-making or prediction or attention policies that are consistent with the things we know. And that can happen in your, when you're not interacting with the world, maybe sleeping, or in a way that doesn't need to interface. I mean, that doesn't need to be related to what we're doing when we're acting in the world and reacting to what's going on in the world. Okay. So that's the main thing, and it's connected to the literature in reinforcement learning on what's called model-based reinforcement learning, where you separate the model from the policy. So that's interesting, because even if you have very little data, which is an issue for like living animals in a new situation, you may be able to afford a lot of compute in order to find what is the right policy to interpret things, to answer questions about that data. And so the model part itself can be pretty compact, pretty small, pretty constrained, but the part that makes inference with that can be as big as you want. The bigger it is, the best, right? So we can have a huge brain and use it even though we are not confronted with a lot of information about the outside world. So we wrote a paper that exploits this ability of GFlowNets to sample from a given reward function to sample from Bayesian posteriors. So one of the things that's interesting, that's coming from neuroscience and cognitive science, is the clues suggesting that the way that humans are making inferences is consistent when we can compute it with the sort of optimal Bayesian inference. And these neural nets, because they learn these policies that sample proportionally to some quantity, can learn to sample from a Bayesian posterior. And that's simply because that quantity you need for a Bayesian posterior is just likelihood times prior, which are easy to compute. Normally, it's intractable to compute those posteriors or sample from them, but these neural nets can learn to do that, and we've shown how to do that in this recent paper last August. Yeah, so one way to make this a little bit more concrete, we can use, and we have used GFlowNets, for example, to construct data structures like graphs, as I said. And the way they would do that is that the policy would sample one action at a time that constructs one, what adds one piece to the graph, right? So here, let's say at some step, you already build this graph with nodes 1, 2, 3, and then the neural net, which in this case in our implementation is a graph neural net because it's convenient, is going to choose which action, like which node or which edge to add, and then we do it, and those choices are stochastic. And now we have a new data structure, and so we sequentially construct these data structures stochastically, of course. All right. Yeah, one thing that's interesting about these GFlowNets is that their training objective is really about local consistency. So in a way that's similar, but also not exactly the same as in the Bellman equation, for those of you who know a bit about reinforcement learning. And that's very, very different from the way that we are training current deep learning typically. I'm not going to explain all these because I don't have enough time. But well, one thing that's maybe interesting for neuroscience is that if we look at the mathematical theory about how they should be trained, the ideal way of training them is not using the samples of the inference machine themselves, but some more noisy samples, right, which cover a flatter, broader distribution. And this may be interesting because dreams are like that we have these somewhat incoherent sequences of elements in our dreams. And actually, it would be useful in this context to have something like this. So we have this ongoing work where we try to exploit this notion of locality in time and extend it to locality in space. So if you think about different pieces of the brain, like little modules that are talking to each other, and you unfold in time their computation. So you've got space on one axis and time on the other, and the arrows indicate how they send information to each other, potentially through a recurrent computation. But now I'm just unfolding it to see what is the computation that is happening. And using the GFlowNet math, you can actually write down how, in a purely feed-forward way, if you want, how these modules should update themselves based on the information they are getting from their inputs and from the modules they're talking to next, just downstream of them. And that's it. There's no backprop at the global level, which is, I've worked for a number of years on a number of alternatives to backprop that could be biologically plausible. And one big problem is just that the brain is too big in terms of timing for information to go back and forth several times in order to get the right credit assignment before the new frame is coming in, right? Every 150 milliseconds or something. And so what's more reasonable is that although you do want to have feedback coming from all across the brain, you want something that's more local that can just require local communication, including feedback connections, in order to be able to train itself, and yet learn something that's globally meaningful. Right? It's not like you're not taking into account what the others are doing because of this consistency objectives that are forcing each of the pieces to learn some computation that is consistent with what its neighbors in time and space are doing. All right. Okay, so time is flying, and let me move on to the last part of my presentation about the relationship with high-level cognition. So I've talked already for a number of years about a hypothesis that my group has been exploring, that a lot of the gap that exists between current state-of-the-art in deep learning and human-level intelligence is due to the fact that we haven't been able to incorporate the functions associated with consciousness. And I have lots of reasons to kind of argue that if we could do that, it would help with things like sample complexity. In other words, how many examples a system needs to learn a task, how many examples it needs to adapt to a new task or a new setting, and how well does it do when things change in the world, what's called out-of-distribution generalization, the ability to make causal connections and reason with that, and to represent knowledge in a compositional way that allows to recombine pieces on the fly as our conscious reasoning allows us to do. And so actually, GFlowNets are trying to fill that gap. But yeah, it's just the beginning. Yeah, so quickly, we know that when humans are faced with these novel settings, like you're driving in a country where you have to drive on the other side of the road compared to what you've been used to, we use our conscious abilities. We pay attention and we think about what we should be doing and repeat ourselves, stay on the left, right? Yeah, there's evidence that this ability to deal with interventions, changes, is connected to our conscious abilities. So, evolutionary, it would be really useful to have those abilities to be able to face novelty as humans are able to. And that's connected to the System 1, System 2 divide that was popularized by Dan Kahneman. It's like if current deep learning is really good at System 1 things, which is happening very fast and involves implicit knowledge, and in parallel, and System 2 kind of abilities are involving conscious processing and explicit knowledge, and things happening sequentially. So in the last few years, we explored a number of, say, classical deep learning architectures to implement some of these inductive biases, some of these particularities that we observe in humans when they perform high-level cognition, such as the modularity of information, the bottleneck of working memory, the fact that working memory has discrete contents, the fact that the dependencies that exist between the high-level concepts that we manipulate in our working memory are sparse. In other words, think about in language, you have a sentence with just a few words that express a dependency that involve very few words, and yet can make a very accurate prediction about one entity given other entities. And that is not something that would be true for pixels, but is something that is true at this high level of representation. The fact that we construct these sequences of thoughts, each involving just very few entities, and the causal interpretation that we have for many of these variables that we're manipulating. So where do GFlowNets come in? So we can think of the transitions in the sequence of transitions that form the computation of a GFlowNet. Remember, in my example, I was constructing a graph sequentially through these transitions where there's an internal action that adds a piece of thought or a thought, right? And so, so we can make that connection. And so what's going on when the GFlowNet chooses a particular transition is a stochastic choice based on a competition between different choices. Now, the choices might be, for example, the choices over all the possible short sentences, like, cat chases mouse. And as was noted by Bars already many decades ago, there's both competition and cooperation going on for the content of working memory. So here, for example, somehow the parts of the brain that know about cats and the parts that know about chasing and the parts that know about mouse are collaborating together to form this conjunction, say cat chases mouse. But of course, they're also competing with all the other guys that are trying to say something else. Right? So this is the kind of thing that you can represent with GFlowNet, that both that competition and that collaboration through represented through how the policy chooses things like these thoughts or these short sentences. And it's, it's related to something that in machine learning we don't know how to do, which is deal with latent variables that are super rich, like all of the sentences that would be potentially true in a given context, without having to sample all of them. And GFlowNets have the computational machinery to allow us to do these sort of things. All right, the last bit I want to talk about, which is related to all this, is how would that policy of choosing like a thought be actually implemented in neural hardware? And the theory that I've been kind of thinking a lot about, and I want to share briefly this morning, is centered on the notion of attractors in the dynamics of the brain. In particular, the part of the dynamics that matters when you have conscious ignition. In other words, when this competition, cooperation is taking place, it doesn't happen in one step of computation. It happens through a differential equation, if you want, or something that happens through time, where you choose, say, one short sentence among a zillion other possible ones. So here, what we want to highlight is that there is evidence that this process of conscious ignition has convergent properties. In other words, the state of the brain is moving towards an attractor, right? And attractors have nice properties. So in particular, their basin of attraction, the regions, if you start from those regions, you get into the attractor. Those regions are form a partition of the space. In other words, you're either in the basin of attraction of one attractor or of another attractor. So you can see that this creates a discretization by its very nature. The fact that you have attractive dynamics means that you have discretization. So that's why here I talk about ineffability of thoughts, which is one of the big mysteries associated with subjective experience and consciousness. The fact that there is something about what we're currently, what's currently going on in our head that we can't quite express with the words that we use when we report of what we're thinking about. And that's very personal, and it depends on our experience, and different people are going to have different internal representations. So the idea is that the attractor state is itself a very high dimensional vector. It's the activity of the brain after you've converged to an attractor, and that's maybe as big as how many neurons you have in your brain, maybe a subset, but still a huge number. Obviously something that you cannot describe in words. It's just too rich. There's no way you can do that, which doesn't mean it's impossible by nature, right? If we have the right instruments, we could observe every neuron in your brain. But me as an agent talking to you, I can't do that. And it may also be that I lose a lot of the information that's present at the moment when I'm thinking it, when this gets stored to long-term memory or short-term memory or something like this, so that when I recollect something, it's not as rich as the first time I felt it, right? So this is interesting because now we see that our conscious thoughts would have, according to this theory, a dual nature. At the same time, the state of the brain corresponding to these attractors is a very, very rich and high-dimensional object. And that's impossible to describe in words. And at the same time, there is a word or there is a sentence. We have this discrete facet. And actually, this is not so different from what we currently do in natural language processing with deep learning, where we have word embeddings, which, by the way, my group initiated in NeurIPS 2000, where a word is both a symbol and an embedding vector or a word vector, right? So the these vectors can be potentially very high dimensional, and they contain information, semantic information, that the symbols themselves don't. So it's not just like an appendage, this representation associated with an attractor. It's something fundamental that helps to carry meaning, and that relates, for example, cat and dog together, even though they're just two different vectors. Also, these attractors in a high dimensional space, they can be organized in a compositional way. So what does that mean? So I gave the example of a sentence with 3 words, like cat chases mouse. So we could imagine that in some dimensions of the space, there's an attractor that's going to converge towards like the part about cat. And in other dimensions, somehow you're converging about the part about mouse, and other dimensions about chase. And there's enough room, if you want, in that high dimensional space to represent all of these attractors and how they interact with each other. So it's really one attractor, but if you look in different dimensions, you may extract specific symbolic entities like individual words. So they can be compositional, which means the number of attractors can be huge. It's not just like in that simple figure, of course. Now, there's another thing that's interesting that relates to cognition. How we go from one thought to the next is not discrete. You know, I think this, stop, think that, stop, think that. No, that's not how it's happening to me, at least. We have this fluid transitions from one thought to another that, you know, it's just going, you know, it's a completely soft thing in time. And how could that be consistent with the picture I just told you? Well, there's I think, a great analogy that is well studied in, actually I studied when I was doing my PhD using neural nets for speech recognition. And we're interested in the vocal tract as a dynamical system. And what's going on when you're speaking is that you have these phonemes that are like the symbols. Think of the phonemes as the sentences in my example. And they're discrete. But what's happening is you don't ever actually reach the configuration in your vocal tract that corresponds to a pure phoneme. What happens is you kind of you know, ski between those muggles, and you never actually reach them. But it's fine, because remember, if you are in a basin of attraction, anybody can like read that off, because they're like unique to each of these discrete entities. So you don't actually need to reach the attractors. And by the way, reaching the attractors in general for most like normal dynamical systems would take infinite time anyways. So you don't want to wait for reaching the attractors. What is sufficient is to sort of get sufficiently into the basin of attraction that an observer, which is like another part of the brain, maybe like the language areas, is able to decode that, oh, you're going into the attractor for the word mouse, right? So then you wouldn't actually need to converge. You would just have these soft transitions where you're like continuously going through these attractors, and then you would have this fluid perception of your own thoughts. And what would make that possible is that this whole dynamics is not static, right? Just like your vocal apparatus is driven, you know, by your brain that changes some knobs so that at any moment, the attractor towards your going might be different than at the previous moment, right? So you've got something which is a policy that controls what you're going to be thinking about, that you're learning. And again, GFlowNets are a nice tool for doing this, that kind of shapes these attractors so that it's going to be these thoughts that are going to dominate rather than other thoughts. The other aspect, and the last one I want to mention, is the stochasticity of thoughts, right? So, you know, the Necker cube is either one way or the other way. And in case you didn't know about it, it's here. And this is very different from the current way we implement attention in deep learning, where we have what we call soft attention. We are actually mixing between all the interpretations in a soft way. But it doesn't seem to be what's going on in your brain when you're thinking, it's that sentence. Of course, there's this fluid aspect, but it's that sentence and it's not another one. So, and there's a bit of randomness, like which of the sentences is going to actually come up. Seems random. It's hard to prove that, but that would be also consistent from a probabilistic inference point of view, that you want to do that. You want to be able to sample stochastically from these potential discrete, mutually exclusive interpretations that are maybe all compatible with the current context. And so you need stochastic hard attention. Stochastic because there's randomness in it, and hard because you take these hard decisions. It's this attractor, not that one. It's this sentence, not that one. It's this interpretation of a cube. And that could be implemented in this randomness. Where would it come from? Because up to now I told you about the picture of the dynamics as if it was deterministic, and a lot of theories about this. But of course now we want randomness, and so that can come from many places. It can come from the noise in synapses. It can come in the noise from firing. It can come from being on the edge of chaos that amplifies any noise, right? All right, so I'll stop here. If you're interested in learning more about GFlowNets, I wrote this tutorial. I encourage you to have a look at. Thanks.
Yoshua. So we have time for a few questions. I think Guillaume is first.
Hi, Yoshua. Thanks for the talk. I have two questions. One is a little bit more technical and one like forward-facing. Regarding your picture of unfolded networks in the brain and the fact that you had this idea of local sort of consistency.
Yes.
Knowing what little I know about GFlowNets in general, I think there's like global consistency equations to be observed, right?
No, you can do it purely from local ones.
You can do it purely locally, even if you build a huge network.
Yes,
you don't need balance.
We call it a detailed balance constraint. And so every little bit of computation can, if every part of the brain at every moment satisfying these constraints, then you've got globally the right thing.
Right. Okay. And then my following question is, do you think how robust are these?
So wait, these are this is the local constraints. So for example, A is sort of a choice made by one module I, and PI are like its parents. And I mean, the ones that it's getting information from, and that's it. And so each of them is computing these functions, but they have to locally satisfy those equations.
All right, cool. I need to look into this a bit more. The second question is, generally speaking, these types of approaches rely on some pretty beautiful mathematics, but I was wondering if you had some ideas of how robust they are. The brain is super noisy. It's very
right.
Like stuff fails all the time.
Yeah.
How much is this really implementable in wetware? Let's just say.
Well, so the nice thing is we've been playing with GFlowNets now for over a year. And of course, we never satisfy those constraints exactly because we train neural nets to approximately satisfy, to minimize the divergence between the left and the right-hand side of these equations. And it works. So even though we don't fully satisfy those constraints, and they're all local, so you don't, this part doesn't care about how badly, some other part is doing. It's trying to do its job to be consistent with its neighbors. And that's it. And of course, you get an approximation. How good it is an empirical kind of question. The more capacity you put in each of these pieces, the better it can make those constraints exact. And there's no like overfitting there because you can, work as much as you can locally to satisfy those constraints.
Thank you.
Well, thank you. Thank you for the talk. I had a few questions. First, how is this different from the FEP and active inference?
What?
How is this different from the FEP and active inference? Also, how do
you... no, I do one question at a time.
Sure, no problem.
Because my working memory is not that great. It's connected to a lot of the literature in variational methods, which active inference is connected to. But there is a problem with variational methods that they tend to, for mathematical reasons, find unimodal solutions. In other words, you're trying to learn a distribution over something like latent interpretations and things like that. And these methods tend to be stuck in like one interpretation or very few when there could be a lot, and you really want to be able to sample all of them. And this thing about dreams that I mentioned is actually a guard against that. So you can train GFlowNets in what's called off-policy way, meaning you can train them using hallucinated samples that are not, under the current model, and that actually helps them to explore the space of configurations in ways that variational methods cannot deal with.
I'd be interested in your take on sophisticated inference then, but how do you derive the discreteness of the state space from first principles?
Well, that's just like, classical math of dynamics, right? So when you have attractive dynamics, meaning convergent dynamics, like if you start from different places, the two states start from different places, they tend to get closer together, then you get attractors. It's the condition. And we observe that phenomenon of convergence in the brain. So, and that's just like very like, I don't know, it dates back to the middle of the 20th century or something. This is like classical stuff.
All right, and my last question, which is extremely related, is what do you think of niche construction as an ecological attractor?
Sorry, do I think of what?
Niche construction as an ecological attractor.
Oh, okay. I'm just thinking about single brains here.
Mm-hmm.
And maybe some of these ideas are related to, the bigger picture of how we interact together, but thanks.
Thank you for the talk. I have two questions, mostly conceptuals. So in the case of the phoneme examples and having like the individual phonies as attractors, I was wondering, because with languages, depending on the language you speak, there are some phonemes that carry meanings in differentiating the word. Like let's say TH, we don't have it in French. So if I just add TH in words instead of T, it just makes me sound funny, but it doesn't affect the meaning.
Right.
So I was wondering, is there some attractors that can, is there like a kind of importance, kind of scales between the attractor that can actually change the meaning of like the global environment versus just like making it a bit different or like, but still like not affecting the overall meaning?
Yeah, so here in what I'm talking about, when I talk about high level consciousness, your brain is making up those attractors. It's learning them, right? It's a result of a learning process so that it performs like, a good modeling of what's going on in the world and optimizes some sort of interesting reward. And so there will be things like what you're saying, some attractors may be redundant in some ways, and so it's hard to picture these high dimensional attractors. And as I said, like you're going to have different things happening in different dimensions. So yeah, I think what you're saying is quite possible.
Okay. And
maybe one question.
Oh yeah, sure.
Okay, I have a question from Dlambo Liu, who's asking, do attractors of different humans need to align softly with each other for us to understand each other?
Right. So again, this is about multiple brains talking to each other. Of course, I mean, obviously we coordinate kind of shared understanding of language. And this is a very interesting process, and I don't have much to like add to that except to say that is very important and needs to be studied. With this notion that each of us really has, I mean, what this says is each of us has a different interpretation of what each word means, but obviously through interaction, we kind of try to synchronize as much as possible, but never perfectly, right? And that's why we have ineffability as well. If your brain and my brain was exactly performing the same thing, then it would be a very different proposition, right? But of course it's not. Okay, well, I think we need to move on, so thank you very much.